Hello students, welcome to the EPG Pathshala. I am Ashok Goel from the Department of Physics and Astrophysics, University of Delhi. Today we are going to talk on the module Symmetry Transformations and their relationship with the conservation laws. That is, the module's name is Symmetry Transformations and Conservation Laws from the paper Classical Mechanics. After completing this module, you will be able to learn about the deep relationship between symmetry and conservation laws. So in fact, whenever you will learn that whenever there is a symmetry in the problem, there is a corresponding conservation law. You will learn about Neother's theorem, which is a very important theorem in quantum field theory, which states that the invariance of Lagrangian under continuous symmetry operation leads to a corresponding conserved quantity. Principle of symmetry transformation plays a key role in the formulation of quantum field theories in many branches of physics, like in modern day particle physics, condensed matter physics, general theory of relativity, string theories, etc. Many of these modern theories are based on symmetry formulation. The conservation laws in physics have a deep relationship with the symmetry operations. The requirement of invariance of the Lagrangian under symmetry transformation so that the physical results remain unchanged leads to conservation laws. In what follows, we will consider some space-time transformations which lead to the corresponding conservation laws. Suppose, for example, we have a Lagrangian of the system which is a function of generalized coordinates and the velocities. We have dropped the subscripts from Q, so Q stands for a set of generalized coordinates, Q dot a set of generalized velocities, and there could be an explicit dependence on time, which we have shown here while writing the Lagrangian. Now, if we now make a transformation of the coordinates from Q to Q prime, which means each generalized coordinates is transformed to corresponding prime coordinates, then the Lagrangian is now expressed in terms of these new coordinates. So we have a new Lagrangian which is a function of the transformed generalized coordinates and the transformed corresponding generalized velocities. So L, which is a function of earlier Q dot T, is now transformed into a new Lagrangian which we represent as L prime, a function of Q prime, Q dot prime and T. Now, the different solutions of Qt which are obtained from L, from the original Lagrangian and from the L prime, must have equivalent trajectories. Why? Because if Q going to Q prime is a transformation under which is a symmetrical transformation, then the different solutions must have equivalent trajectories. Now, the transformation of coordinates can be either discrete or continuous. We now give examples of some discrete transformations and continuous transformation. Consider mirror reflection. Under mirror reflection, the coordinate x goes to x prime, which is reflected and is minus x. The coordinate y goes to y prime, is equal to minus y, and the coordinate z goes to z prime, is equal to minus z. So this mirror reflection is an example of a transformation which is discrete, in which the component goes to minus its value. We can also have a translational transformation in which, for example, we translate the component x to x prime, where x prime is given by x plus some fixed value a, and y goes to y prime is equal to y, let us say, and z is equal to z prime is equal to z. That is, x is translated from the point x to x plus a, keeping y and z fixed. On the other hand, a transformation is continuous if the transformed coordinates have a continuous dependence on a suitable parameter defining that transformation. The simplest example of a continuous transformation is a rotational transformation about the z-axis. So consider a vector r to be rotated about the z-axis such that when it's rotated by an angle theta, x component of the vector r goes to x prime given by x cosine theta plus y sine theta. Y prime goes to minus x sine theta plus y cos theta, and the component z prime remains the same. So we will now discuss how space-time translational symmetry leads to the conservation of energy and linear momentum. The key idea is that the space is assumed to be homogeneous and isotropic. So what it means? It means that a physical system at one place in space and time develops the same way at any other space and time point. For example, if I do or observe a physical phenomena here today, then if the same experiment is done tomorrow or 10 days from today at some other place, then I should observe the same thing. So this is the meaning of the isotropy and homogeneous nature of space and time. So let us consider a Lagrangian of a dynamical system of n particles. Now this Lagrangian is a function of position coordinates and velocities. We further assume that the constraints are holonomic. Then the Lagrangian can be written as L is a function of that only the coordinates and the velocities, and it is written as the difference between the kinetic energy and the potential energy. Potential energy in term, because system is conservative, is a function only of the coordinates. Now, potential does not depend on the velocities. Now, if the symmetry under space translation is considered, that means that if from a point R, I translate everything to the point R prime, which is separated from the point R by some vector A. That means R goes to R prime, which is equal to R minus A, where A is a constant vector. So under this translation, let's assume our Lagrangian L transforms to, it becomes L plus delta L, where the change in the Lagrangian delta L, because of this change in the coordinates R going to R prime, is then clearly delta L is equal to sum over I delta L by delta Ri dot A. If the Lagrangian remains invariant under a transformation, that means the physical results remain unchanged, which means that delta L is equal to 0. So delta L is equal to 0 and alpha is an arbitrary parameter. Therefore, this implies dl by dri sum over I is equal to 0. Now, from the Lagrangian equation of motion, we have then ddt of sigma over I dl by dri dot is equal to 0. For a particle moving in the conservative force field, the Lagrangian is given by half mi ri dot square sum over I minus the potential energy, which is a function of Ri. Therefore, the partial derivative of L with respect to Ri dot is simply equal to mi Ri dot, which is nothing but the sum of the linear momenta Pi's. And from the condition of invariance of the Lagrangian, namely ddt of sigma over I dl dri dot is equal to 0, we obtain then ddt of sigma pi is equal to 0. Sigma pi is the sum of the momenta. That means the sum of the momenta remains constant. So we have the important result that the total linear momentum of the system is conserved. Now, if the motion of the system is described by a set of generalized coordinates given by the set qk, we can define a quantity pi as a partial derivative of L with respect to qi dot as generalized momenta, all the momentum conjugate to the generalized coordinate qi. That is, the momenta conjugate to a generalized coordinate qi is defined as dl by dqi dot. In general, the conjugate momenta may not be identical to the mechanical momentum, and remember that mechanical momentum have the dimensions of MLT inverse, but a generalized coordinate does not have or need not have the dimension of Cartesian coordinate. Therefore, generalized momenta will also may not have the dimensions of a Cartesian or mechanical momentum. So in terms of generalized force, which is defined as Fi, that is force acting on the generalized coordinate I as the partial derivative of the potential energy with respect to the generalized coordinate I, the Lagrangian equation we have is ddt of dl by dri dot is equal to pi dot is equal to Fi. So this becomes the Lagrangian equation. Now, if in the expression of the Lagrangian, it so happens that a particular coordinate QL does not appear explicitly. So when you write down the expression for the Lagrangian, which is which is kinetic energy minus the potential energy, and if a particular coordinate in it does not appear explicitly, then this coordinate is called a cyclic coordinate or ignorable. And in that case, obviously, since the coordinate does not appear explicitly in the expression for the Lagrangian function as well as in the potential, so the partial derivative for u or L with respect to this cyclic variable is 0, and therefore the ddt of the corresponding momenta is equal to 0, as the momentum conjugate to cyclic coordinate is conserved and is a constant of motion. So this is an important result and this is very useful. So a look at the expression for the Lagrangian tells you that which is a cyclic coordinate if the coordinate doesn't appear explicitly in the expression. Then you immediately know that the momentum conjugate to this cyclic coordinate is conserved and is a constant of motion. So we have seen that under a translation in space, the linear momentum is conserved. Now let us consider the symmetry under the time translation. Under time translation, t goes to t prime, which is equal to t plus delta t. And therefore, the Lagrangian is transformed from L to L plus delta L, where delta L is equal to partial derivative of L with respect to t into delta t. If the Lagrangian remains invariant under time translation, then delta L is equal to 0, which means that the partial derivative of L with respect to t is equal to 0. Now the total derivative of L with respect to t is given in terms of the chain rule, since L is a function of the coordinates and the velocities. So dl by dt is sigma over I dl by dri by dt plus dl by dri dot plus dri dot by dt plus the partial derivative of L with respect to t if it depends explicitly on time. So this can be written using the Lagrangian equation as sigma over I ddt of dl by dri dot into dri by dt plus dl by dri dot by dt plus dl by dt. Therefore, dl by dt is equal to ddt sum over I, the total derivative with respect to t of dl by dri dot ri dot plus the partial derivative of L with respect to time. This can be cast in the form that d dt of the difference of L minus sigma over I of dl by ri dot is equal to minus dl by dt is equal to 0. Now L is equal to t minus u. T is equal to half sigma over I mi ri dot ri dot minus u of ri. Therefore, dl by dri dot is simply mi by ri dot. Since the u does not depend on the velocity, we assume u not to depend on the velocity. Therefore, d dt of L minus mi ri dot ri can be written as d dt of t, where L is equal to t minus u, minus sigma over I mi ri dot ri, which is equal to 2t. Therefore, you have d dt of t minus u minus 2t is equal to 0, which implies d dt of t plus u is equal to 0, which in turn implies that the total energy is conserved. So, what have we learned? We have learned that if Lagrangian remains invariant under time translation, then the total energy is conserved. If it remains invariant under space translation, then there is the linear momentum that is conserved. Let us now consider rotational symmetry. Now, rotational symmetry we expect arises because of the isotropy of space. If I do the experiment at one angle and I do it at some other angle, the space is isotropic, there should not be any difference. So let us see what happens if we demand that there is a rotational symmetry in mechanics. So let us consider a position vector r which rotates about the z-axis, and let r rotates by an infinitesimal amount by angle delta theta around the z-axis and takes up the position r prime. Then if you look at the diagram, that means the tip of the vector r is moving on a circle of radius r sine theta, and this infinitesimal displacement delta r, that is a difference between the vector r prime and r, is given by r times delta theta, with delta theta is the infinitesimal rotation, and remember that delta theta we have taken as a vector, and this is along the z-axis. So the change in the position vector when it rotates by the angles theta can be written as delta r is equal to r vector r cross delta theta. While considering the invariance under rotation, so we have considered the rotation around the z-axis, and therefore the position vector r goes to r prime, and for an infinitesimal rotation this is equal to r plus delta r, where delta r is obtained by infinitesimal rotation in the plane perpendicular to the z-axis. So delta r is delta theta into r, as is clear from the diagram. Then the Lagrange's equation is given by d dt of dl dri dot minus dl by dri is equal to 0, and under the rotation as L, the Lagrangian goes to L prime plus delta L, then delta L is equal to dl by dri plus dl by dri dot, which is equal to sigma over I. dl by dri using the Lagrangian equation is d dt of dl by dri dot, and dri is equal to delta theta cross ri, and substituting for delta ri dot, then this can be written as delta L can be written as sigma over I ddt of dl by dri dot into delta theta cross ri minus dl by dri dot into delta theta cross ri dot. Now dl by dri dot is equal to pi, that is momentum conjugate to the position vector ri. Therefore, the change in the Lagrangian under rotation is equal to sigma over I pi dot delta theta cross ri plus pi dot delta theta cross ri dot, which can be written as sigma over I delta theta dot r cross pi plus ri dot cross pi, where we have used the property of the triple scalar product, and then delta L can be cast in the form delta L is equal to sigma over I delta theta dot ddt of Ri cross Pi. Now, if the Lagrangian remains invariant under rotation, then delta L is equal to 0. Then it remains invariant under arbitrary rotations, so delta theta is arbitrary. So that would mean that sum over I ddt of R cross Pi is equal to 0. But what is R cross P? R cross P is the angular momentum. So Ri cross Pi is the angular momentum of the ith particle. Therefore, the invariance of the Lagrangian under a rotation says that the ddt of sum of the angular momentum of each particle is equal to 0. The ddt of sigma over I Li is equal to 0, which means the total angular momentum is conserved. So what is the symmetry we have used? The symmetry we have used that the Lagrangian is invariant under the rotation. And this is justified because of the isotropy of space. Now let us talk about Neother's theorem, which I said is one of the most important theorems in quantum field theory. Suppose we have a Lagrangian which depends on the generalized coordinates and generalized velocities, and let it also depend on the time t. That L is a function of the set of generalized coordinates qk, generalized velocity qk dot and t. And let there be continuous symmetry operation S. The symmetry operation S, let us say, depends on a set of parameters alpha k, and let's say the symmetry operation also depends explicitly on time t. As an example, the symmetry operation of rotation about the z-axis is parameterized by a continuous angle of rotation theta. The transformed Lagrangian L prime then is a function of the symmetry transformation S, which is a function of alpha and t, and S dot, which again is a function of alpha and t. That is, L prime now is equal to L, which is a function of S alpha t and S dot alpha t, and could also be a function of t explicitly, and this chain must be equal to 0. So if S alpha t is a symmetry operation of the system, then we must have dds, that is the derivative with respect to the symmetry operation of the Lagrangian, equal to 0. Now, the total derivative of the Lagrangian with respect to the symmetry operation S can be written as dl by ds into ds by d alpha plus dl by ds dot plus ds dot by d alpha is equal to 0 by the same chain rule, because now L is a function of the symmetry operation S and S dot, which in turn depend on the parameter alpha and time t. So continuing the discussion of Neother's theorem, in the previous equation, we now use the Euler-Lagrangian equation that is ddt of dl by ds dot is equal to dl by ds, and we use this to replace dl by ds in the previous equation, and we get the total time derivative of the partial derivative of L with respect to S dot multiplied by ds by d alpha plus dl by ds dot into ds dot by d alpha is equal to 0, which can be written as ddt of dl by ds dot into ds by d alpha equal to 0. So we thus have the product of the partial derivative of L with respect to S dot with the partial derivative of S with respect to alpha a constant. We can therefore define a quantity I of j, which is a function of the set of generalized coordinates and the velocities, as sum over k dl by dsk dot multiplied by dsk by alpha j in the limit alpha j's go to 0 as equal to constant. Since why we can do that? Because our equation 330, namely dl by ds dot into ds by d alpha is equal to constant, holds for all alphas. Therefore, this quantity ij defined in this form is a constant, and this is the celebrated Neother's theorem. So Neother's theorem states that if a Lagrangian is invariant under a continuous symmetry operation, which is parametrized in general by m parameters alpha 1, alpha 2, alpha m, then the theorem states there are exactly m conserved quantities associated with the symmetry transformations. This theorem forms the cornerstone in the development of quantum field theory. Let us consider the example of a system whose Lagrangian is given by L is equal to half sigma over I mi ri dot square plus ri square theta I dot square plus zi dot square minus ur. That is, the system consists of, let us say, n particles of mass m1, m2, and we have used the cylindrical coordinates r, theta, and z to represent their position, and this system is in the force field given by the potential u of r. So we have chosen r, theta, and z to be the generalized coordinates, and we have further assumed that the potential depends only on r. The Lagrangian does not involve the coordinates theta and z. Therefore, from the expression of the Lagrangian, we immediately see that theta and z are the cyclic coordinates. Therefore, the momenta conjugate to theta and z are conserved. So, momenta conjugate to theta is p theta, which is dl by d theta dot, can be easily calculated, is mi ri square theta I dot is equal to the z component of the angular momentum. That is the angular momentum of the system about the z-axis. Why? Because Lz is defined as sigma over I mi ri cross vi with the z component, which is sum over I mi vi is ri dot, or the z component of that, which is mi xi dot vi dot minus yi xi dot. And when we express r theta, we can express now x, y, and z in terms of generalized coordinates r, theta, and z. Namely, x is equal to r cos theta, y is equal to r sin theta, z is equal to z. Therefore, Lz can be immediately seen to be equal to sigma mi ri square theta I dot. So, for this Lagrangian, which is expressed in terms of cylindrical coordinates moving in the force field whose potential does not depend on the coordinates theta and z but only depends on r, the angular momentum or the z-axis of the system can be expressed as Lz is equal to sigma mi ri square theta I dot, and the momentum conjugate to z, that is pz, is dl by dz dot is mi zi dot, is nothing but the linear momentum of the system along the z-axis. Thus, in this example, where the particle moves in a force field which is independent, or which is only a central force field, depends only on r, then the linear as well as the angular momentum of the system about the z-axis are conserved. So students, let us now summarize what we have learned in this module. What we have learned is that the homogeneity and isotropy of space. Homogeneity means physics or the laws of nature do not depend whether the experiment is done here or there, that they are the same. Isotropy means that the space, if the orientation is rotated in space, it should not matter. So homogeneity and isotropy of space leads to the conservation of energy and linear momentum and angular momentum, as we show in the table. Now, if the symmetry is a space translation, which is a result of homogeneity of the space, in that case, the Lagrangian is invariant under space transition, that if I make a transition from one point to another, then the Lagrangian is invariant, and that leads to the conservation of linear momentum. The homogeneity of time leads to a symmetry, which is the time translational symmetry, which says that the Lagrangian is invariant under translation in time, and there is no explicit dependence on time, then the total energy is conserved. Finally, the isotropy of space leads to a rotational symmetry, which means that the Lagrangian is invariant under rotation, and that gives rise to the conservation of angular momentum. So, there are 7 constraints, that is integrals of motion, for a closed system. What are these 7 constraints? The total energy is conserved. Since linear momentum is conserved, in 3-dimensional Euclidean space, there are 3 components of linear momentum. So 3 plus 1, and then angular momentum is conserved, and angular momentum is also a vector. So there are 3 components of angular momentum. So there are 7 conserved quantities. So if the Lagrangian is invariant under a continuous transformation parameterized by m parameters, then according to Neother's theorem, there are further m conserved quantities associated with these symmetry transformations. Thank you.